Now we have a U-shaped tube with some cross-sectional area, 1 centimeter squared, and it's half filled with water. So just to make sure you understand what we're talking about here, that's a U. That is a U-shaped tube. The little cross-sectional area there is the 1 centimeter squared, half filled with water. So at first, it's just got water in it up to about there. And then what happens is we half filled with water, and now, period, 9 mils of oil are added to one side. And what's going to happen? So if we pour oil on here, one thing is oil and water don't mix, maybe you've heard. So the oil won't mix into the water, it'll remain its own column sitting on top of the water, but it's going to push that down. And if that goes down, that has to go up. So after we add the oil, it'll still be a U, like that. But relative to the initial position, let's see, the water will go up because the oil went down. And then here's the 9 mils of oil. All right, push it down, push it up. All right, how high does the water level rise? So we want to know, how far up does it go? Let's see. So this is a hydrostatics problem. This was static. We put this in. It's static again. So we're just asking what is the new condition? So it's definitely a statics problem. It's a tricky one because we have two fluids. That's what makes them tricky. Or if we have stacks of fluids, things like that. But it's still just a hydrostatic problem, and you're going to use the hydrostatic equation, and you're going to use horizontal lines to figure out what's going on. Your intuition may say this isn't possible. These have to be at the same level. Anytime you have a fluid like that, it has to become level. That's only if it's a single fluid. When it was all water, these have to be level. If you have different fluids of different densities that aren't mixing, then you can actually have a height like that. Both of these exposed to atmospheric pressure be different because the fluids have different densities. So this drawing is correct. Let's see. So what we want to do in this case, if you're not sure what to do, is look at it and say, how high is the fluid? And think, well, I could calculate things. Let's think of things we could calculate. We could definitely calculate the pressure right there because we're going over a column of oil, and we could just use the hydrostatic pressure equation and say atmospheric pressure plus the density of oil times gravity times the height of that column. So that's one thing we could calculate. It's also useful to think about where could you draw a hydrostatic, like a horizontal line, and say the pressures are equal. So let's see, here would not be good because that's going into the air. Here would not be good because although it's good here, the atmospheric pressure there, here you've changed fluids. So these lines are only useful when you're in the same fluid. So the line you care about is here. If you go here, then you know the pressure there, and you know the pressure there because it's being pushed down by the oil. So this is what we're going to go for. And coincidentally, this kind of looks like the height you want, right? That's how much the water was pushed up, or it's at least related to the height you want. So let's do this pressure on either side. And then you see, this is interesting. It's just the hydrostatic pressure there is equal to here, and this is just a column here for the height we're looking for. So equating these two pressures calculated from the column of the fluid should give us an equation that might get us to the answer, how high it is. All right, so let's do that. So let's see. Let's do it left and right just to make it nice. So on the left, the pressure here, big P, equals atmospheric pressure plus rho GD, the density of water, G, and then this, how deep it is H. That's what we called it, rho water GH. On the right, so this is the left, and now on the right, we have also atmospheric pressure on the top. These are both open to the air, plus rho of oil, G, and then actually we're going to need this. All right, we'll call that D. So we can think of what do we know? Well, whoops, it's a plus there. is the atmospheres don't matter. It's the same on both sides. We know the densities of water and oil. We know G. We know little g. But then if we're looking for H, we need D. But there is actually more information here. That's the reason it told us it's 9 mils of water. And it's a 1 centimeter squared cross-sectional area. Because you know, as we do a little aside here, 9 mils is 9 centimeters cubed. So if you have this column of oil that is 9 centimeters cubed, then, and the cross-sectional area is A, and then the volume is that A times the depth D, right circular cylinder volume. So it's 1 centimeter cubed squared is the area times D. So you can see if that's equal to 9 centimeters cubed, you can see D is 9 centimeters. Right? 9 times 1 is 9. So now we actually do know D. Right? So we know everything here except H. So now we can plug in real quick 1,000 MKS units, 9.8. H we're looking for times 700 MKS units times 9.8. Oh, that goes away. Times 0.09 meters. There you go. 7/10 of 0.09. So what you get is that this H is 0.0. It's 73 meters. And in our online system, it asks for it in centimeters. It would be 7.3 centimeters. But that's not the answer, right? Because we were asked, now just to give a little bit of geometry, there's always a twist at the end. We were asked, how high does the water level rise? We weren't asked how much higher is the water level over the interface between the water and the oil. So for that, you'd need to go back to the beginning. Where was it? And how much did it rise? And what's going to happen is if it gets pushed down a certain distance, it's going to have to be pushed up the same distance. And because of the continuity equation, we usually use it for flow rates, for A times V equals A times V. You can also just use it in statics just for a volume. The volume equals the volume. So whatever volume gets pushed down has to get pushed up. So what that's telling us is that this whole thing is H, but it goes up by H over 2 from its original height, because this is also H over 2. Because the original height has to be halfway between how far it got pushed down, has to be equal to how far it gets pushed up because of continuity. So the answer is actually half of that, 0.0315 meters, or 3.15 centimeters. So that's how you deal with multiple fluids in a static situation like this, is especially if it's in some tube where you have different arms, is definitely look for hydrostatic, these flat lines you can draw where you know everything. And don't get freaked out by things that look wrong, because remember, when you have different fluid densities, things get crazy.